Hello my friends, welcome again to my video channel. Today we will locate the problem on the passband tuning board of this TR7. The owner told me that there is, after some hours of operation, the problem. So obviously the PBT does things which it shouldn't do. It shifts the frequency. The sound is the pitch is very high, as if the filter shifted to the end of like an RTGY setting, which is a very high frequency, and it cannot be adjusted, neither with the passband tuning or the other settings, USB, LSB and so on. So he switched off the transceiver, switched it on again, and then it worked again. Okay. Difficult to find such a fault. We need a mouse trap to catch it. Well, how does this mouse trap work? First, some connection points. We have here the input from the pots on the power supply board, which set the bands for this BFO. That's a BFO. For the different modes, AM, RTGY, CW and so on, we have different voltages resulting in different frequencies. I just focus on LSB and USB. This voltage is set by the mode switch, and it can be measured here on this meter, and it is derived from the board. This point, this is a ground connection, and you see when I switch from USB to LSB, we hear a buzz. Ignore the buzz, we see that the voltage changes, and for other modes it also changes. Let's go back to USB. The signal tracer again is in the test mode. That means when a signal is on the output, the signal tracer does nothing, and when the signal disappears, when it falls under the threshold we can see here, then it makes an alarm. This happens when I switch from USB to LSB. Watch the S meter. This means the signal is shifted. I have a CW filter in it, very narrow filter. Signal disappears and I have the alarm. When I switch back to USB, everything is okay. So if there is a problem anywhere in this range here, this area, with this voltage or with the frequency of the oscillator, then we can hear the buzz as an alarm, because this frequency shifts out of the passband tuning. When the passband tuning, I can do it also by hand. When I shift the frequency out of the range, when it's okay, would be the same as switch it off and leave it in USB. Second connection here is a frequency counter. You can see in the background. It's connected to the 1 megohm input times 10. We have a 10 megohm impedance, and the frequency is measured at this point. The emitter follower, the counter is connected to here, where we actually have in USB mode 13.6935 69349. Okay, that's not important. Well, and now I wait what happens, whether the frequency shifts when we have suddenly a buzz or whatever happens. What's the reason? Is it the voltage? This voltage here, it could indicate a problem in these switches here, these analog switches. 4016 is an analog switch. Maybe this has a problem. I already had a TR7 many years ago where this board of this IC was faulty. I had to swap it. Maybe it's also the case, but I want to measure it to be sure what the reason is. It's also possible that the problem is in this circuit with the cap diode, the varicap here, the crystal itself, or other components here which cause a frequency jump. We will see what happens. The mouse trap is activated, it is set, and now I wait. And while we are waiting on the reaction of the TR7 and the passband tuning, we can check another thing. This is the input protection of the receive circuit. There is such a component installed. You know what it is? So-called gas discharge tube. It's an overvoltage protection, a discharge unit, which is triggered from a certain voltage level, and it is located here in this input, but it's not shown in the diagram. It's located here, where we have external antenna, where we have the external antenna connection and the external receiver connection. There's in general a jumper between, and here on the external antenna there we have this discharge unit, this tube to ground, and in parallel there's an inductor also to ground. It is not shown here, it is not shown in the other diagrams. Maybe it was added later, maybe after killed a lot of double balanced string mixers as we had here. Anyhow, this has the task to prevent overvoltage coming in over the antenna in the receive path. The power amplifier has no discharge unit in this path, it is only in the receive path here. And the inductor to ground prevents against static charge on the antenna. For example, ground plane antennas are in general isolated from ground, they could charge up. And if there's a transient overvoltage caused by any lightnings nearby, a direct hit of course is not protected, but any nearby lightning strokes can cause high voltages by magnetic or capacitive coupling. And this is prevented by this little unit. I took it out and I check it whether it is, maybe it is damaged or pre-damaged by the stroke we had. I assume it was an overvoltage in the antenna stroke, in the antenna circuit by a stroke or so. I'm not sure, but it could have been. The owner confirmed it a little bit that there was some overvoltage, and he didn't really know whether he disconnected the antenna or not. Always disconnect the antenna. Well, let's have a look at the data sheet. Here we have the data sheet of this CG series. The unit is a ZG90L. L is only an indication of the wires. And the data, we can have a look at them here. CG90. Hope you can read it, yes. It has a DC voltage of typically 90 volt. Minimum is 72, maximum 108. This is for low voltage rise, 100 volt per second. This is more or less a varying DC voltage. And here we see the problem of this gas-filled tube. When we have a high slew rate, 100 volt per microsecond, then the thresher voltage or breakdown voltage rises up to 400 volt. And when we have 1 kilovolt per microsecond, then we have 600 volt. And lightning strokes are always in the range of microseconds. Then we are here and not here. So it can be dangerous. On the other hand, we have the low pass filter in series, and depending upon the band setting, the slew rate of course is reduced by the low pass filter. So this will help a little bit, but in general we have not a perfect protection with this unit. Other informations here are regarding the lifetime. The surge life are 400 shots, but for higher currents up in the range of 4 kiloamp, there's one application, and then this unit is bad when it ever sees a current of 4 kiloamps, but there were no 4 kiloamps. We would see this in the transceiver. Okay, I will now check it with a variable DC voltage connected to this discharge unit with a series resistor and see when it starts to conduct. This is a test setup, my homemade power supply up to 400 volt DC. I'm using it in the range of 300 volt, full scale is 300 volt, that's sufficient. The discharge tube is connected via a series resistor with 1 megohm to the output to limit the current. I only want to see whether it triggers whether it starts to conduct. The voltage is measured, of course, across this unit, indicated here. So we have, especially in case of triggering, a difference between this voltage here and the voltage here. But this voltage is a relevant voltage. It shows the voltage across the tube, discharge tube, and not this voltage here. This voltage is only for energizing the circuit. Again, 1 megohm series resistor. The input is 10 megohm, so we have an error of approximately 10%. Well, now let's start. I increase the voltage, and again it should trigger around about 90 volt DC. So we have 38, 40, this is a 100 volt scale, 51, 60, 70, 80. Now I think it has triggered. Yes, we are at 140. Again. $69, $70. Current is limited. I assume we have an instability here, similar to a sawtooth generator. There's a capacity, and when it triggers, the voltage drops down to 0 or similar. Then it charges up again over this megohm, and then it triggers again. So this generates a sawtooth, which is a known principle since I think more than 100 years. But it indicates that this discharge tube is okay, and there is no problem. Yes, it has triggered. Now we're at 150 volt, only 64, 65. That's okay, this tube is good, and I will solder it again into the transceiver. You know the dentist effect? Nothing happens. Since 3 days, and I would say 10 or 12 hours per day, this TR7 is operating. Nothing happened. I observed the signal here on the phono output, stable as a rock with a calibrator. Passband tuning is okay, as it should, no problem. I touch the board, nothing happens. I treated it with heat, with a heat gun, with a cold spray, ice spray again. Nothing happened. Contacts are okay. Switches are okay when I check it. Sorry, passband tuning is in. It reacts as it should. The switch passband tuning is clean. No problems. What to do now? I will swap 2 components. First, I will swap this analog switch, MC14016, or it's a 4016, 4 times analog switch. I will swap this cap diode, this varicap. It's an MV209. It's the same diode which made trouble in the VCO board, you remember. And of course I will take out this resistor. The fault could be here, yes, but I don't think so. This crystal is okay. I tapped on it, mechanical vibration, nothing happened. And I treated all these components with heat and cold, as I said, nothing happened. So if there is a problem, it is here or here or here. The coil doesn't have a problem. I checked all the solder connections, wires, traces, and so on. And here on this side, no. The mode switch is okay. We have here a stable voltages when switching between the different modes. So really, I assume the problem is this resistor or this varicap. But I will take out this analog switch also. And yes, of course, there is a risk. Maybe the new components which I bring in are worse than the old ones which I take out. It could be, as we say, a shoot into the knee. I hope not, but I have no other idea what to do. So I will start with this work. The MV209 is out and new. The 22K resistance series also. This is to set the frequency of the oscillator of the BFO together with this coil. It has to be realigned, but the difference is nearly zero. I just tested it in the TR7, the frequency relation, the PBT is nearly the same, only some 100 Hertz drift. That's okay. Now we have to take out this one. There are different methods. I use in this case, the method pin by pin. I will pinch off all the pins and take it out pin by pin. It's not necessary to save this IC. When we say it is not okay, then we have to swap it and to throw it away. So it's the easiest way, because the pads are not damaged when doing it in this way. Using any desoldering gun and desolder wick and so is possible, yes, of course. But these old boards are rather touchy and sensitive against high temperature and soldering too long on a board or on the pins. So I do it pin by pin. I take this one. This is okay. This is very slim, but rather stable. I have another one which also could do this job, but it's a little bit sensitive. The blades are a little bit weak for this purpose. So I will take this one and pinch it off pin by pin. Okay, this was one side, and now the other side. And now we can take out pin by pin using a tweezer or plier or similar. Hold it from one side, solder it on the rear side. Then we can take it out pin by pin. It's the easiest and the best way in such a case. And you see the pins are not damaged, not on this side, not on the other side. And now the solder can be taken away pin by pin with a desoldering pump or some braid. It's much easier because the pins are out, and then we can look for the IC socket. The IC socket is in. Index is of course on the right side. The last optical check on the bottom. All pins are soldered, no shorts, no damage of the traces, nothing. It's all okay. There's one pin which needs a ground connection on the other side. I checked it with the continuity meter. It's okay. There is a ground connection. This pad was a little bit damaged, but if the solder went in sufficiently to make a safe contact. Now we can insert the new IC and bring it back into the transceiver and see what happens. The new IC is a CD4016, same type, CMOS is in, and as you can hear it works, and we can switch the modes. We have different pitch. Of course the difference between LSB and USB has to be realigned, because the new varicap has a little bit different capacity, some picofarad plus or minus. But in general, RGGY has a high pitch, CW, LSB, and when I go to passband tuning, I can tune it manually. Okay, I will realign it according to the manual. These are the trim pots I have to set new, because we have a new varicap in it. So the oscillator has to be realigned with these trim pots. Not a big deal. Takes about 15 minutes or so. There's another big question. Is the problem solved or not? I have to admit, I don't know. I did my best what I can do. Again, I will do a long time test as I made before. and look what happens, whether the passband tuning now is stable or not. I think it will be stable, but the question is, did I cure the problem? Again, I don't know. Was there a problem? As I understood the owner, there was a problem, and I think I also have heard for some seconds when I did it the last time. But again, I said it, I was not sure. Before I was in my basement, it was too late. I was too slow. So this problem wasn't there any longer. If it was there, anyhow, I will do another long time test. That's all I can do after I realigned it. Another important topic, this is valid for all boards in the TR7 and in the R7 also in the receiver. The wires here have to be cut very short because the board is inserted and it comes very close to the shielding. Especially here you can see it, where we had the problem with the, was it the VCO board or second mixer, I don't remember. Sometimes these red distance holders are missing. It is important that they are already in place, still in place, so this board cannot move. And have a look at it flat over the board against the white paper. Check whether wires are too big, and if you have any doubt, simply cut it. Another important test is simply move the board around, especially try to squeeze it against the shield. Whether there is a problem, we don't have a problem. Same is valid for the other ones. Whether you can create a short and then you would hurt a problem in the signal or not. But it's obviously okay. Now we can do the realignment. The alignment is done. The cover, the shield is in place. I checked the output power, it has 100 watt on 10 meter, a little bit less as before. Now we have here a signal of 0.2 microvolt in the 10 meter band. You can hear it. In SSB bandwidth. When we go to CW bandwidth, of course we have a better signal to noise ratio. That's it. Now we are at the end of this project with this TR7. I spoke to the owner and we decided to stop this project. It makes no sense to waste more time and effort looking for a fault which is most probably not present any longer. The passband tuning is cured, that's my personal opinion. We swapped the analog switch, the varicap and the resistor, which are the most probably problems in the passband tuning. If there should be a fault again, it will maybe happen. Why not? By the way, this transceiver is more than 40 years old, so there's always a danger that a fault will occur. So he can send it back to me. He lives in Germany also, and it's not so expensive to send it back. It can be paid. Other countries would be more expensive, but we have no trouble with customs and so. The fault was indeed only the balanced mixer, the ring mixer, and the one of the switching diodes in the input of the high pass filter, where the calibrator is connected. It looks like it was an overvoltage coming in the transceiver via the antenna connection, by a thunderstorm. I cannot say it by sure, of course. It could be. Whenever there is a thunderstorm or anything else, lightnings, disconnect the antenna, of course. It's a standard procedure. Don't forget to ground your antenna. And a hint, there is an overvoltage protection, as we have seen, which only is active for voltages above 60 volt. This is a little bit bad protection. There's a second antenna input for the VLF reception, and there's absolutely no protection against overvoltage. There's only a series resistor, I think it's 1 kilo ohm, and then the antenna is connected via a low pass filter, 30 megahertz, directly to the double balanced mixer, which was bad. So when you have a long wire antenna for long and medium wave reception and connected to the input, to the VLF input via the auxiliary contact on the rear side of the transceiver, not via the antenna, the BNC, there's a second input on the auxiliary contacts. This auxiliary contact is not protected, and it's a very sure way to kill the ring mixer again. Disconnect this antenna in case of troubles outside. That's my proposal. Well, that's the end. I hope you enjoyed it. Stay healthy, stay tuned, see you on this channel.